You are dying. You have been alone for 47 years. No warmth, no sound, nothing in any direction for billions of kilometers. Your heartbeat is a nuclear ember, a fistful of decaying plutonium keeping your circuits alive. And every day, a little more of that heat disappears into the void. But you are carrying something. Data. 47 years of it. Measurements from the boundary where our sun's influence ends and the true interstellar void begins. Data that took our species a lifetime to collect. Data that cannot be recreated, cannot be replaced. So you do the only thing you can. You point your dish, a 3.5-meter circle of aluminium about the size of a dining room table, toward a pale blue speck 24 billion kilometers away. You fire your signal at the speed of light, and you wait. 22.5 hours later, your signal finally reaches Earth. And the dish is busy. There's a queue. Over 40 spacecraft, all screaming at the same 14 antennas. The James Webb Space Telescope is on the line. Perseverance is in the middle of a drill sequence. A Mars orbiter is mid-download. You, the farthest object humanity has ever launched, the machine carrying our golden record, our message to the stars, our declaration that we exist. You wait. That was fiction. But here is what is not. Voyager 1 is real. The 22.5-hour signal delay is real. The queue is real. Right now, over 40 active spacecraft are competing for time on just 14 antennas. Demand already exceeds supply by 40%. And one of only 3 70-meter dishes on the entire planet has been offline since September 2025 and won't return until October 2028. The solar system has a bottleneck. It is on the ground, and it is cracking. Welcome to Space with William. Before we go anywhere, I need to plant 3 things in your brain. First, how do 14 antennas manage over 40 spacecraft spread across billions of kilometers? Second, there is a $1.4 billion spacecraft that had its primary antenna fail before it even reached its destination and still returned 70% of its planned science using a backup barely more capable than a garage door remote. How? Third, NASA's own Inspector General has confirmed that by the early 2030s, demand for antenna time will exceed capacity by 50%, meaning someone, right now, is already deciding which missions get to speak and which go silent forever. Who is making that call? Hold all 3. We answer every one. Think about the last time you were at a massive, sold-out stadium concert. Bars on your phone are full, but you can't send a single text. The network is saturated. Everyone is trying to talk at once. Now imagine that concert is the entire solar system, and there are only 3 ground stations for the whole thing. That is the Deep Space Network, or the DSN. Built by NASA's Jet Propulsion Laboratory starting in the early 1960s, it consists of 3 ground stations positioned roughly 120 degrees apart around the Earth. One in Goldstone, California in the Mojave Desert, one near Madrid, Spain, and one near Canberra, Australia. As our planet rotates, at least one station is always facing any given point in the sky. We never lose sight of the stars. Each station houses a collection of antennas. The crown jewels are the 70-meter dishes, massive structures taller than a 20-story building, capable of detecting signals so faint they carry less energy than a single snowflake landing on your hand. The signal power arriving at Earth from Voyager 1 is roughly 10 to the negative 16 watts. That is a decimal point, 15 zeros, and then a 1. That is the kind of engineering we are talking about. The signals travel at the speed of light. Sounds fast until you grasp how big the solar system actually is. A message to the moon takes about 1.3 seconds. To Mars, depending on orbital positions, 3 to 20 loud minutes. A command to Voyager 1 takes over 22.5 hours each way. Nearly a 2-day round trip for a single exchange. But the speed of light isn't the real bottleneck. Antenna time is. Each large antenna can only track one spacecraft at a time. Missions submit requests weeks in advance through a process that looks less like rocket science and more like booking a conference room in the world's most overbooked office building. Imagine a hospital with 3 telephone lines for every patient, every doctor, every emergency. Now imagine the patients are scattered across different planets. The calls take hours to connect, and the line goes dead if you look away. That is the Deep Space Network in the 2020s. In 2022, the DSN supplied 77,000 hours of antenna time. It was not enough. Demand exceeded capacity by 40%. NASA's Inspector General confirmed it in a public audit. 1 in every 3 hours of requested antenna time simply not being fulfilled. And the budget to fix it? Cut. The DSN's operating budget fell from $250 million in 2010 to $213 million in 2024, while the mission count doubled. Then September 2025 arrived. The 70-meter Goldstone antenna, DSS-14, one of only 3 such dishes on the planet, over-rotated during a test, snapping internal cables. It has been offline since. Engineers confirmed the damage was so extensive that it will not return until October 2028. 2 years. Gone. During the most congested period in DSN history. Drop this in the comments. If NASA had to choose between Voyager 1, Perseverance, and the James Webb Space Telescope for the very last available antenna slot, which one do you save? And why? In 2020, a routine command was sent to Voyager 2, roughly 12.5 billion miles from Earth. The command triggered a minor calibration, but something went wrong. The spacecraft's antenna tilted about 2 degrees off alignment with Earth. 2 degrees. That is nothing when you are adjusting a picture on your wall. It is everything when your signal has to cross 12 billion miles of empty space to hit a dish that, from that distance, is smaller than a grain of sand. Voyager 2 went effectively silent. Not dead, just pointed the wrong way. And the only antenna powerful enough to send a corrective command was the 70-meter dish at Canberra. It was offline for upgrades. Engineers scrambled. They managed to send a carefully crafted shout through a smaller dish, but it took multiple attempts over weeks before Voyager 2 finally turned its antenna back toward home. One of humanity's most important scientific instruments was functionally unreachable. Not because of some cosmic disaster, because of a scheduling conflict with a maintenance window on one antenna. In April 1991, the Galileo spacecraft, $1.4 billion, heading for Jupiter, had its high-gain antenna fail to deploy. 3 of its 18 ribs were stuck. The mission's primary communication system was dead. All that remained was a small backup capable of 8 to 16 bits per second, the speed of a telegram, from Jupiter. What JPL did next belongs in every engineering school on Earth. They remotely reprogrammed Galileo's onboard computer across hundreds of millions of kilometers to compress data by a factor of 10. They electronically linked radio telescopes around the world into a combined receiving array far more sensitive than any single dish. Through that improvised, brilliantly re-engineered pipeline, they recovered 70% of planned science, including strong evidence for a liquid water ocean beneath the ice of Europa. one of the most consequential findings in the history of planetary science. Through a backup antenna barely more capable than a garage door remote. The list of upcoming missions is staggering. Artemis is building a permanent presence around the Moon. Mars Sample Return aims to bring physical samples to Earth for the first time. Europa Clipper is heading to Jupiter to search for life. Japan's MMX mission targets the moons of Mars. ESA's JUICE is already en route to Jupiter's icy worlds. India, China, South Korea, the UAE, all expanding deep space ambitions. Every single one needs ground station time, and the DSN has not added a new full-scale station since it was originally built. The network was designed for 5 to 10 simultaneous missions. It is handling over 40. Within the next decade, that number could double, and when crewed missions reach Mars in the 2030s, with 22-minute delays and human lives at stake, they will depend on this same network, the one that is currently 40% over capacity with a broken antenna on a shrinking budget. The people who run the DSN know this is unsustainable, and they have been working on something that could change everything. It is called optical communication. Instead of broad, messy radio waves, you use laser light to carry data. Imagine trying to hit a target with a flashlight from a mile away. The light spreads. It's hard to tell where the center is. That is radio. Now imagine a high-powered laser pointer. The beam stays tight, focused, and carries vastly more information per second. In late 2023, NASA launched DSOC, the Deep Space Optical Communications Experiment, aboard the Psyche spacecraft. It successfully demonstrated laser communication from deep space, transmitting data from over 200 million kilometers at 10 to 100 times the data rate of traditional radio. The technology is proven, but it is not operational. Lasers require incredibly precise pointing. A tiny vibration and the beam misses the ground receiver entirely. Unlike radio, lasers cannot punch through clouds. A rainy day in California and the window slams shut. The real solution is not replacing radio with lasers. It is building a hybrid system. Radio for reliability, lasers for bandwidth. Alongside optical upgrades, engineers are designing arrayed antenna systems, clusters of smaller dishes working together with more flexibility and redundancy. International antenna sharing agreements with ESA, JAXA, and ISRO are being negotiated. Machine learning scheduling is already squeezing more useful time from existing hardware. And there is a long-term vision being studied seriously. Relay satellites at gravitational equilibrium points throughout the solar system. An interplanetary internet backbone, where a spacecraft at Saturn does not have to scream all the way back to Earth. Every one of these solutions is real. Every one is being pursued. None of them fully mature before 2030. Let me leave you with one thing I cannot stop thinking about. Voyager 1 carries a golden record. A 12-inch gold-plated disc containing sounds and images selected to represent humanity. Music, laughter, rain. A mother's first words to her child. Our message to the cosmos. Our proof that we were here. Voyager 1's power source will fade to silence somewhere in the early 2030s. When that moment approaches, engineers will need to book a DSN window to receive its final transmission. They will submit that request months in advance. They will negotiate for the slot in a queue alongside 40 other missions. The machine carrying humanity's message to the stars will need to get in line to say goodbye. Every photograph you have ever seen from another world, every discovery that made you feel small and amazed at the same time, every headline about water on Mars or rings around Neptune, every single one of those moments traveled as a whisper through empty space and was caught by a dish in a desert. 3 deserts. 3 sets of ears. That is the entire infrastructure connecting human curiosity to the rest of the universe. The universe is not silent. It is practically screaming with data, with discovery, with answers to questions we have not even thought to ask. But we build a very small ear. The missions are launching. The data is piling up. The question is whether the ground can keep up with the sky. The universe is speaking. Build the ears. If this surprised you, if you had no idea NASA's solar system pipeline was running 40% over capacity with a broken antenna and a budget that has been shrinking for 15 years, subscribe. This is what we do here every week. Next, watch how NASA's laser experiment just shattered every record in deep space data transfer. That video is right here.